After we have studied the molecular orbitals for different kinds of molecules and we have studied what color actually is, what's being absorbed and observed, now it's about time that we try to understand and describe in a more quantitative way the color and properties of coordination compounds. And we will start with an example that I'm sure you're very familiar with. The oxygenated blood contains in the hemoglobin protein iron, which has an oxygen bound to it. However, the deoxygenated blood contains iron in the hemoglobin protein, but now it has water. For the fact of changing this ligand, the color changes. You are familiar that oxygenated blood is red and deoxygenated blood is actually more blue. And you have this kind of device that it's a tiny spectrophotometer that measures how red your blood is, and using Beer-Lambert's law, it can tell you the amount of oxygenated hemoglobin you have, therefore telling you the level of oxygen that you have. The question is, why is it that when iron has oxygenated has oxygen coordinated to it, it's oxygenated iron, it has a color different than when is water coordinated to the iron. So to do that, we will have to introduce something called the crystal field theory. The crystal field theory is nothing else but a simplification of molecular orbital diagrams. In this slide, you see the molecular orbital diagram of octahedral complex. Vanadium 3 plus is a D2, that is, it has 2 electrons and is surrounded by 6 waters. Each water carries 2 electrons, so you have 6 waters, you have 12 electrons. In total, you need to be able to place 14 electrons. So if you count, you have 2 here, 4, 6, 8, 10, 12, and the 2 go up here. So notice that these are pretty much these electrons pretty much belong to water, and the 2 electrons are mostly the metal. So the crystal field theory will focus between the HOMO and the LUMO. We'll focus in these 2 molecular orbital energy levels that actually is the 3D or the d orbitals, it could be a 4D or 5D, that stop being degenerated and they are now split in 2 different levels. So crystal field theory tries to explain in what way these 5D orbitals are split now in 2 different levels. Notice that the color can only be explained in transitions between these 2 now they're not degenerated anymore, between these 2 HOMO and LUMO orbitals. The other transitions, the ones that you see here and here, these electronic transitions would fall into the ultraviolet and they cannot explain color. However, transitions between the HOMO and the LUMO, between these molecular orbitals, these do explain color. So let's try to understand crystal field theory, which is nothing else but a simplification of the whole molecular orbital diagram and focuses on what the d orbitals look like once you approach, in this case it's octahedral, so once you approach 6 ligands around them. So first of all, we have to remember that the d orbitals are, unless you approach ligands around them, they are degenerated, they have the same energy. However, the energy of the d orbitals will change as you approach ligands, and that will strongly depend on the geometry of those d orbitals. So let's try to examine that. This is only for octahedral complexes, so when you have 6 ligands. So notice, so let me go back here, that each ligand carries 2 electrons, okay? And the d orbitals will contain as many electrons as your metal has. Okay, so now let's see what happens if you approach the ligand, each of them carrying 2 electrons, to our d orbitals. So let's see. In here you have 2 of the d orbitals, 2 out of the 5, and notice that if each ligand carries 2 electrons here and 2 here, well, if you place the vanadium electrons, remember that we want to place the vanadium electrons here in our d orbitals, well, there will be repulsion, right? Because if you place an electron here or or an electron here, there will be the repulsion between the electrons of the ligand and the electrons of the metal. So these will be more unstable than if the ligands were not approaching to it. However, notice that the other three d orbitals, if you approach, notice that there is no overlap for any of these. So this means that the repulsion is lower than these up here. Therefore, these three will be more stable than these two up here. This means that now we can explain why the 3D orbitals that were supposed to have the same energy now are split in two levels. In a repulsion set of the orbitals, and in one in which the repulsion is more minimized, these other three. And remember, that's only true for octahedral complexes, because I am approaching 6 ligands at the same time. So this is the 3D orbitals, that they have the same energy. As you approach 6 ligands, you remember that you have the set of 3, these down here, of 3D orbitals that are more stable, and the ones in which the repulsion is more remarkable, therefore they'll be more unstable. And the split among these two sets of d orbitals is characterized as delta. In this case, it's delta OH, coming from octahedral, and this exclusively depends on the ligand. So let's try to understand what this means. So the ligands that are on the left side of this list will have a small split. That is, remember, we're talking about we had 5 d orbitals that had the same energy. You approach 6 ligands, and now these 5 d orbitals split in 2 groups. The difference between these 2 groups is characterized as the delta, and this delta will be stronger if the ligand is on the right side of this list. So that will have a larger split. This list of ligands is called the spectrochemical series, and it has been found exclusively experimentally. So right now we do not have the tools to explain why is it that carbon monoxide or cyanide create this larger gap than iodide or bromide, but we'll have to take it for granted now, just as observed experimentally. So what kind of questions we can answer with the information that we have described so far? Well, in this case, we are given 4 different coordination complexes. Notice that all of them are cobalt 3 plus, and if you go to the periodic table, cobalt 3 plus is a D6, okay, and you have to place 6 electrons, and so typically we can put them here. We will see if that can change, but the distance between the 2 sets of d orbitals, this delta, will be smaller or larger depending on the ligand. So now let's observe these 4 complexes. In one complex, let's call it 1, it has all ammonia. The other one, complex number 2, it has all ammonia except 1 chlorine. Complex number 3, oh, this is number 3, it is all ammonia except, you're not going to see anything here, but it has water instead of a chlorine. And in here it has, in our complex number 4, it has 2 chlorines. So can we talk about which compound will have the largest split? Well, if you notice, ammonia, we have either ammonia, we have water, or we have chloride. The complex number 1 has 6 ammonias. So the split will be larger in complex number 1 because you have 6 ammonias. Now, the one complex number 2 will be second because it has 2 chlorines, or I should say chlorides, because they become charged. And I apologize. No, because water. So complex number 3, instead of ammonia, has water. So notice that in the series, water is before the chloride. Therefore, we'll have a larger split than number 2, because number 2 has only one chloride. And finally, number 4 will have the smallest of the split. So this is the largest split, the largest delta, and this is the smallest delta. Now, can that explain color? Well, let's see. The one that is orange-yellow, it absorbs in the blue. I'm doing it here, so if you see it orange, it's because it absorbs in the blue. Followed by the number 3 that absorbs in the red, therefore it is green. Followed by purple. If it's purple, or you would say violet, it absorbs in the yellow. And finally, number 4 is green. It will absorb in the red. Notice that this explains the trend that the larger the gap, the higher the frequency of the color needed to excite this electron. So the higher this, so that means that the higher the frequency, the more energetic the photon needs to be to promote an electron from the HOMO to the LUMO. Now we can explain color, and we can say it in a more quantitative way as for how many ligands in the whole spectrochemical series we have. This tool will keep giving us more results also in terms of magnetism that we will explore in the next video.